Continuing the discussion on critical minerals and their role in energy transitions, we left off in the middle in the previous podcast, just to keep these, reasonably short. Clean energy technologies defied the COVID-19 crisis with strong growth, making 2020 a pivotal year for clean energy transition. So that's the good news. The bad news, of course, is that the emissions are still continuing to rise and show no bend, and in fact, the COVID impact on lowering the CO2 emissions by something like 7% globally have now ramped back up, and we are headed right back to ever increasing, accelerating emissions globally. Change in energy demand and car sales by type in 2020 relative to 2019. So energy demand was down for oil, coal, gas, nuclear, but modern renewables were up, and car sales, total car sales were down, but electric cars were up considerably, almost 40% here. Good news. But achieving climate goals requires a further rapid acceleration in clean energy deployment. So looking at annual deployment of clean energy technologies by scenario in gigawatts, here in terms of electric networks in kilometers and electric car sales in millions. In the stated energy policy scenario and sustainable development scenario, we need to ramp up to 3 times by 2040 in the sustainable development, and somewhat less for the what will be reached is the stated energy policy scenario. And for wind, so that's for solar, for wind it has to ramp up by 3 times in the sustainable development scenario compared to 2019. Electricity networks have to go up 3 times in the 2040 sustainable development scenario. Stated energy policy scenario will only get us to about 2 times. And in terms of electric car sales, we have to go up compared to 2020 by 25 times, over more than 70 million here, and this is just under 6,000 kilometers here. In terms of gigawatts, it has to reach almost 325 or so by 2040 for the sustainable development scenario. The rapid deployment of these technologies as part of energy transitions implies a significant increase in demand for minerals. We already looked at this, so I won't go into details. Electric cars, conventional cars, power generation in kilograms per megawatt, we already looked at for the various energy sources. Mineral requirement for new power generation capacity has increased by 50% since 2010 as low carbon technologies take a growing share of the investment. So just comparing historical data from 2010 to 2019, you can see that kilogram hour per megawatt has gone from around 4,000 in 2010 to over 6,000 by 2019, and here share of low carbon in new power generation capacity is shown here in terms of percentages. But the message is clear, with the largest jump here coming for copper again, as we saw before, and then there are others. Yellow is the silicon for solar. Current production of many energy transition minerals is more geographically concentrated than that of oil or natural gas. So already saw this as well, so let's not repeat that. The level of concentration is similarly high for processing operations, with China's significant presence across the board. So as various issues play out with alliances between Russia and China, China's economic ambitions and its ambition in terms of being, a military power, maybe I shouldn't say that, but whatever the ambitions are, concentration of resources and processing is obviously something that everybody has to worry about. And you can see that China is a big player in all of these in terms of processing for copper, lithium, nickel, cobalt, and rare earth elements. Total mineral demand from clean energy technology is set to double in the stated energy policy scenarios and quadruple if we want to stay on sustainable development scenario by 2040. So here we are from 2010 to 2020, and where we need to be for 2040 steps and 2040 sustainable development for hydrogen electricity networks, EVs and battery storage, other low carbon power generation, wind and solar PV, in terms of millions of tons of mineral demand. Okay, exploitation of mineral resources gives rise to a variety of environmental and social implications that must be carefully managed to ensure reliable supplies. I am not sure I'll read all of them, but selected environmental and social challenges related to energy transition minerals, environment and social here. Climate change, land use, water management, waste, governance, health and safety, and human rights are the main items looked at. And example here, for example, declining ore quality can lead to a major increase in mining waste, which is almost already happening now. For example, tailings waste rocks. Tailings dam failure can cause large-scale environmental disasters. For example, Brumadinho dam collapse in Brazil. Mining and mineral processing generate hazardous waste like heavy metals and radioactive material. Under human rights, for example, we have mineral exploitation may lead to adverse impacts on the local population, such as child labor or forced labor. For example, children have been found to be present at about 30% of cobalt mining sites in the Democratic Republic of Congo. Changes in the community associated with mining may also have an unequal impact on women. Rising electricity demand alongside much higher shares of wind and solar PV requires a significant expansion of electricity networks. So there are systemic changes needed. This is the annual average grid expansion and replacement needs by scenario in thousands of kilometers, going from drivers and types in 2018 to 2020 to 2030, 40, and for the stated policies and sustainable development policies. Distribution is a big player in the sustainable development in both cases, and increases, and expansion is the other big item here in terms of drivers of addition and type of grid. Okay. There are also AC/DC issues, alternating and direct currents and their transmission. Growing need for grid expansion underpins a doubling of annual demand for copper and aluminum by 2040 in the sustainable development scenario. So in terms of millions of tons, demand for copper and aluminum for electricity grids. So here is aluminum and here is copper for distribution, transmission, and transformer. So again, the message is same, that for both scenarios by 2040 we need significantly more minerals. Additional switching to aluminum for underground cables and wider uptake of direct current system can alter the material requirements considerably. We're not discussing AC versus DC here in terms of generation, transmission, and the system demands, but just looking at the numbers, you can see copper and aluminum demand for electricity networks in the sustainable development under alternative cases. So this is additional switching to aluminum, high aluminum and high DC here, going again from base cases in 2030 to 2040. So high aluminum requires many more million tons of aluminum by 2040, and adoption of DC requires actually lower amounts of minerals in millions of tons compared to the base case. So that's the advantage basically of adding more DC. EVs use around 6 times more minerals than conventional vehicles. So I won't go into the details here, which we have already mentioned. So if you look at kilograms per vehicle of copper, lithium, nickel, manganese, cobalt, graphite, and REEs, which are the remaining rare earth elements, so you can see the various numbers here in terms of kilograms per vehicle, so you can look those up. Electrolyzers that supply hydrogen and fuel cells that use it in vehicles are both major growth areas in sustainable development scenario and present different mineral requirements. So electrolyzers, fuel cells, gigawatt here numbers very different. Electrolyzers at 1600, whereas fuel cells at 24,000 1,000. So this is for steps and this is for SDS. SDS here surprisingly requires a little bit lower than steps, so one has to but it requires more of the sorry, I'm reading it long. In the sustainable development scenario, fuel cells requires less than electrolyzers, and the steps requires more than SDS here for 2050. Okay, just keep those in mind. Hydrogen electrolyzers and fuel cells could drive up demand for nickel, platinum, and other minerals, but the market effects will depend on the shares of the different electrolyzer types. Okay, I won't go into the details, but electrolyzers are essentially for producing hydrogen, and there is a lot of discussion about green hydrogen, blue hydrogen, and various other colors, so you have to read up on that. I've discussed a little bit elsewhere. Alkaline electrolyzer, SOEC electrolyzer, which is solid oxide electrolysis fuel cells, solid oxide fuel cell. PM is the proton exchange membrane, and fuel cell here. So you can see the minerals: nickel, zirconium, lanthanum, yttrium, palladium, platinum, iridium, and so on. So just follow them up. Meeting primary demand in sustainable development requires strong growth in investment to bring forward new supply sources over the next decade. So looking at production in terms of under construction and operating, and primary demand from steps and SDS, you can see that copper, lithium, and cobalt. Copper is going to drop off by 2030 in terms of under construction and operating, whereas both scenarios required more and more in terms of millions of tons. Lithium will grow tremendously in terms of kilotons of lithium carbonate equivalent. So these are committed mine production and primary demand for selected minerals. So the sustainable development will require many more kilotons of lithium compared to SDS, but the mining operations here in terms of production will level off by 2030. Similarly for cobalt, sustainable development scenario requires many more kilotons, almost double the steps scenario here, and the production will also level off in terms of millions of tons. There is no shortage of resources. Economically viable reserves have been growing despite continued production growth, but as we said before, there is the issue of the quality of the ores impacts on enhanced mining and water quality, air quality, ESG issues, environmental, social governance, inequalities, disparate effects on women, etc., child labor, and so on and so forth. So if you look at the numbers, lithium has gone up, nickel has gone up, copper has gone up, all in terms of millions of tons. And sorry, these are the production here in the right axis, and reserves in terms of the reddish magenta, whatever color this is, line here. Climate risk. Mining assets are exposed to growing climate risks and water stress. So you can see that countries that are mining are countries, especially in Northwest India, for example, here, and Western Asia, Middle East. They are Sahara here. They are incredibly highly water stressed. So you can see here the risks range from low in some regions to extremely high, more than 80% over these red colors. So water stress levels are defined as in the Aqueduct 3.0 dataset according to the ratio of total water withdrawals over the total available surface and groundwater supplies. Bad news, of course. Recycled input rates for selected metals and minerals. So what do we have since 2010? Lead is done well, very toxic material. Aluminum, not so high. Cobalt remains low, and the copper recycling is also not very high. These are going to become more and more critical, as well as battery recycling. The amount of spent EV and storage batteries reaching the end of their first life is expected to surge after 2030 as we are ramping up transformation to EV, reaching 1.3 terawatt hours by 2040 in the sustainable development. So this is amount of spent lithium ion batteries for EVs and storage by applications in the sustainable development in gigawatt hours out to 2040, and this is for energy storage, electric trucks, electric buses, electric 2 and 3 wheelers, and of course electric cars dominate, and the step scenario is down here, but SDS is way up here in terms of battery recycling. So amount of spent EV and storage will reach almost 3 times to 4 times the values of 2035 by 2040. So there is a exponential growth after 2030. Emissions from minerals development do not negate the climate advantage of clean energy. So one has to be very careful in terms of tons of CO2 equivalent per vehicle over lifetime. Looking at battery electric vehicles and ICE, fossil fuel. So in other words, there are greenhouse gas emissions involved in production to processing to use of the critical minerals, and the caveat here is that emissions from minerals development do not negate the climate advantage of clean energy technologies. That means they are still far less than mining for fossil fuels, so we have to go ahead with these. The carbon footprint of the electricity mix and the pace of future decarbonization have significant impact on the emissions profile of mineral productions. So this is electricity generation mix of 2019 for various regions: European Union, US, Canada, Chile, China, Australia, and Indonesia. And coal is tremendously high contributor still in China, even Australia and Indonesia, but even the most progressive countries have not weaned themselves out of coal. But you can see natural gas is lower emission, oil, nuclear is always good, renewables are high in some places. European Union, Canada is very high, but Chile is remarkably high, but not so high for Australia and Indonesia. So out to 2040, the emissions intensity of power generation under the current policy context drop off. But again, the question is that fast enough in terms of grams of CO2 per kilowatt hour? Okay. International coordination on sustainable and responsible extraction already exists. Implementation, monitoring, verification, reporting will be critical, but there are various initiatives that focus on climate, sustainability, responsible sourcing, rights of workers, fairness and inclusivity, governance, and security of supply. So it's good. Various names here like World Bank Climate Smart Mining Initiative, Responsible Minerals Foundation, OECD Responsible Business Conduct, Women's Rights and Mining. So the orange ones here correspond to technical assistance. Whatever this color is, purplish color, is for industry standardization. Investment and funding is also included in some, and research and analysis is a part of many of these as well. Okay, so that gives you a sense that there is a lot of reasons to be optimistic about the availability of resources in terms of critical minerals for energy transitions. There are many issues to be worked out along the way, but news is good in terms of the mechanisms already being in place. But one has to keep an eye on unintended consequences of mining for these, as well as concentrated resources and processing facilities, and the perturbations or resilience of the supply chains to unexpected events like the pandemic, for example, or wars, and just political hegemonies which may force one country to hold on to the resources instead of sharing. So hopefully the global community will come together and make it a mission to work together and develop these minerals in a sustainable way and transition the energy systems to renewables completely, and electric vehicles and so on by net zero 2050 or even earlier in terms of sustainable development scenarios. Okay.